Hello everyone. Well, today we will having our new topic to discuss. But before that, let me introduce to you myself. My name is Jayan Derama from BSN Mathematics 3A. Formally start to our discussion, let me introduce to you our participants. Present the decline and revival of learning, we have Jurian Derama from BSN Math. Saying about the Liber Abacai and Liber Quadratorium, we have Miss Marilyn Braga, and to be followed by Miss Kristen May Dumanda, and her topic are the Fibonacci sequence and the Fibonacci and Pythagorean. Overall, our topic is all about the first awakening Fibonacci. The introduction, the decline and revival of learning Fibonacci. Next is the Dark Ages. First, church played a big part in learning monasteries in school. Second, Charlemagne in 742 to 814 appointed Alcorn of York his educational advisor very successful. Every abbey and monastery should have its own school that teach arithmetic, geometry, astronomy, music, grammar, and rhetoric and logic. Next is Carolingian minuscule proportion and readable script that could be easily written and read by the source of our written alphabet. Next is the little emphasis of placed on math. First, more place in rhetoric and literacy. Second, even inclined elements were not prevalent. Third, shift from monastery schools to Catholic schools. Next is invasion of Arab and transformation to Arabic learning. Next is translated Greek, science and math. Next is Arabs were the great scholars at that time. And lastly, Hindus had an interest in arithmetic and algebra. Next is Gerard of Cremona, the Italian translator of scientific book from Arabic into Latin. He worked into the Toledo, Spain and obtained the Arabic book in the libraries at Toledo. Next is the Adelard of Bath. In 12th century English natural philosopher, he is known both for his original works and for translating many important Greek and Arab scientific works of astrology, astronomy, philosophy, and mathematics into Latin from Arabic version which were then introduced to Western.
Here, the 6.2, the Liber Abaci and the Liber Quadratum. The Indo-Arabic numerals. This is the 10 symbols that represents numbers in decimal number system. They originated in India in the 6th or 7th century and were introduced to Europe through the writings of Middle Eastern mathematicians, especially Al-Khwarizmi and Al-Kindi about the 12th century. This is Leonardo of Pisa, the greatest mathematician of Middle Ages, better known by his other name, Fibonacci, son of Bonacia. As a young man, he traveled widely in the countries of the Mediterranean, observing and analyzing the arithmetical system used in the commerce of the different countries. He quickly recognized the innermost advantages of the Indo-Arabic decimal systems with its positional notation and zero symbols. Fibonacci wrote his famous Liber Abaci, in which he explained the virtues of this number system in order that the Latin race might no longer be a descent in that knowledge. These are the written number symbols appeared in the India before the dawn of the Christian era. These include the 3rd century BC, Brahmi 2nd century, Devanagari 8th century, West Arab Gobar 10th century, and last, Spain 976. Fibonacci Liber Quadraturum. The Liber Quadraturum is a book of squares. This is devoted entirely to the Euclidean equations of second degree. In the dedication, Fibonacci related that he had been presented to the Emperor Frederick II at court at the one of Frederick retinue, a certain John of Palermo.
So good day everyone, my name is Kristen May Dumanda. In today's discussion, I will discuss the continuation of chapter 6, which is the first awakening Fibonacci. So here, I will discuss the 6.3 and 6.4. So the 6.3 here that I will discuss is the Fibonacci sequence. So what is Fibonacci sequence? So when we say Fibonacci sequence, this is a sequence in which each number is the sum of the previous two, or in which number is the sum of the two preceding ones. So one of the example of Fibonacci sequence is the Liber-Abaci's rabbit problem. So Liber-Abaci's, this is a book of calculations, historic Latin manuscript of arithmetic by Leonardo F. Pisa, posthumously known as Fibonacci. So here, as we can see, this person is Edward Lucas, a 19th century French number theorist. And it is ironic that Fibonacci is remembered today mainly because of this person who attached his name to a sequence that appeared in trivial problem in the Liber-Abaci's. So here, I have following problem that deal with the number of offspring of a pair of rabbit. So this is the example of Fibonacci numbers. So here, a man put one pair of rabbits in a certain place entirely surrounded by a wall. So the question is, how many pairs of rabbit can be produced from that pair in a year? If the nature of this rabbit is such that every month each pair bears a new pair, which from the second month on becomes productive. So here, as we can see in the table, there are 377 pairs of rabbit, growth of rabbit colony in just 1 year or 12 months. So how can we get this 377? So first, di ba merong taong naglagay ng pairs of rabbit, ng isang pairs of rabbit in a certain place. So after 1 month, yung nilagay ng man doon is nag-bears ng 1 pairs of rabbit. So in the last month, meron na tayong 3 pairs of rabbit. I mean, 2 pairs of rabbit. So, yung dalawa dito, after a 2 month, yung isang original is nag-bears ulit. So, meron na tayong 2 plus 1 is just equals to 3. So, in last month, meron na tayong 3 pairs of rabbit. So, after 3 months, di ba meron na tayong 3 pairs of rabbit doon. Yung dalawa is adult na at yung isa is hindi pa. Kasi nga, 1 month pa yung isa dito. So, yung 2 pairs of rabbit dito is nag-bears. So, 3 plus 2 is just equals to 5. Next month or 4 months, meron na tayong 5 pairs of rabbit, di ba? So, yung 3 dito is adult pairs at yung 2 dito is young pair. So, yung 3 pairs of rabbit is nag-bears ng 3. So, meron tayong 5 plus 3 is just equals to 8. So, another month, same procedure. Yung adult pairs lang yung pwedeng mag-bears at yung young pairs is hindi pa. Kasi 1 month old pa lang sila. So, ang pwedeng mag-bears dito is yung 2 month lang. So, as we can see, after 12 months, meron na tayong 333. So, yung 333 is mayroong 144 adults at mayroong 89 young pairs. So, yung 144 dito is yun lang ang pwedeng mag-pairs. So, 233 plus 144 is just equals to 377. So, when we continued indefinitely, the sequence is like this. So, here, wait. So, here, the sequence is like this. 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on and so on. So, this is we called as Fibonacci number. Fibonacci sequence. So, to find the third term or the 2 here, we need to add the previous 2, right? Yung sinabi ko kanina na to find the third term, we need to add the previous 2. So, what is the previous 2 here? The 1 and 1. So, 1 plus 1 is just equals to 2. And to find the 3 here or the fourth term, so we need to add the previous 2 here. So, what is the previous 2? The 1 and 2. So, 1 plus 2 is just equals to 3. Then, 5, same pa rin. I-add natin yung dalawa. So, 2 plus 3 is just equals to 5. Ganyan lang pagkuha. Very simple. So, next, So this person is Albert Gerard. So here, the Fibonacci sequence is one of the earliest recursive sequences in mathematical work. So what is recursive sequences? So when we say recursive sequences, this means infinite sequence of numbers. So infinite, hindi natin alam kung saan ito magtatapos. So Fibonacci himself was probably aware of the recursive nature of his sequence, but not until in 1634, because this day Albert Gerard had made sufficient progress. This person also who write the formula in his posthumously published work Il Arithmetic de Simon Stephen de Broggs. So according to these ages, sinasabi nila na 8-minute have escaped your attention that successive terms of Fibonacci sequence are relatively prime, and sinasabi nila na we will establish this next. So what is relatively prime? So relatively prime, this means that there is no common factor except 1. So there meron silang theorem na sinasabi dito. So sinabi nila na no two consecutive Fibonacci numbers f sub n and f sub n plus 1 have factor d is greater than 1. So, walang dalawang two consecutive Fibonacci numbers ng f sub n and f sub n plus 1 na greater than 1 yung factor niya. So, let's say, ito yung sequence natin, 1, 1, 2, 3, 5, 8, 13, and so on and so forth. So, here, let's say na yung 1 dito, yung first term natin is yung f sub n. So, what do we call the second term or yung 1 ulit? So, tinatawag natin ito na f sub n plus 1. So, next, yung 2 dito is tinatawag din natin na f sub n plus 2. Yung 3 dito is tinatawag natin f sub n plus 3. Then, next, f sub n plus 4, f sub n plus 5, and so on and so forth. So, how about yung 5 dito is magiging f sub n? So, anong tawag sa 8 dito? So, yung 8 dito is tinatawag natin na f sub n plus 1.
Yung 13, f sub n plus 2, and so on and so forth.
So, how about yung before sa 5, yung 3? So, tinatawag natin na 3 na f sub n negative 1. Yung 2, f sub n negative 2. Yung 1, f sub n negative 3. Gets? So, here. So, proof. Suppose that d is greater 1, then divides f sub n and f sub n plus 1. So, then their difference, f sub n plus 1 minus f sub n is just equals to f sub n minus 2, right? This f sub n plus 1 minus f sub n equals f sub n minus 2 will be also divisible by d. So, from this and the formula f sub n minus f sub n minus 1 is just equals to f sub n minus 2, right? Yung f sub n natin, i-minus natin sa f sub n minus 1 is magre-result ng f sub n minus 2. So, for example, ang ating f sub n is 3. So, yung maging f sub n minus 1 natin is 2. So, 3 minus 2 is just equals to f sub n minus 2 or yung 1. So, 3 minus 2 is just equals to 1. So, it can be concluded that d divides f sub n minus 1. So, working backward, we can show that f sub n minus 3, f sub n minus 4, and so on and so forth. So, our f sub n here are all divisible by d. So, but f sub 1 is just equals to 1, which is certainly not divisible any d is greater than 1, right? So, the contradiction invalidates our supposition and therefore proves the theorem. So, next, if we prove yung isang theorem, mapuprove din natin tong pangalawang theorem. Kasi sinasabi dito na any two consecutive Fibonacci numbers are relatively prime. So, yung dalawang two consecutive Fibonacci daw numbers are relatively prime. So, sinasabi ko kanina, yung relatively prime is there is no factor except 1. So, if we use the GCD, it will be like this. So, GCD, close open parenthesis, f sub n plus 1 and f sub n is just equals to 1. So, here our sequence. So, number 1, let's say our f sub 1 natin is 1. So, ang yung f sub n din natin is 1. So, the factor of the GCD natin ng 1 and 1 is just equals to 1. So, we are proved that the two consecutive Fibonacci numbers are relatively prime. There is no factor except 1 lang. So, next, f sub n plus 1 is 13. So, our f sub n din natin is magiging 8. So, the GCD of 13 and 8 is just equals to 1. So, walang factor ang 13 and 8. 1 lang po. So, how about yung malaking number? Try natin yung malaking number. So, number 3. So, yung f sub n plus 1 natin is 89. So, yung f sub n natin is 55. So, the GCD of 89 and 55 is just equals to 1 kasi walang GCD ang 89 and 55. So, yung higher number nga yung gagamitin natin. Let's say, yung 377 and 233. So, what is the GCD of these two? So, 1 pa rin. So, we are proved that any two consecutive Fibonacci numbers are relatively prime. Next, to verify our contention, let us take GCD A and B. So, let's say, ang A natin is f sub n plus 2 at yung B natin is f sub n plus 1. So, we will use the Euclidean algorithm for obtaining the GCD f sub n plus 1 and f sub n plus 2. So, here, the following system of equation is this. So, to find the f sub n plus 2, we need to multiply first the f sub n plus 1 sa 1, then plus the f sub n. Then, yung f sub n plus 1, to find it, we need to multiply first our f sub n sa 1, then add yung f sub n minus 1. So, let's, and so on and so forth. So, here, as we can see, let's say, yung f sub 8 natin is 21, and then yung f sub 7 natin is 13. So, 21, to get the 21, we need to multiply the 13 and 1, then add the 8, right? 8 here is our remainder, or 8 here is our f sub 6.
Yung 13 is our f sub 7.
So, 13 times 1 plus 8 is just equals to 21.
So, to find the 13,
Multiply the 8 and 1, or the f sub 6 sa 1, then add the f sub 5. So, 1 times 8 plus 5 is just equals to 13, and so on and so forth. As we can see in the last part, to find the 2, we need to multiply the 2 times 1 plus 0. So, you know that, recall that the last non-zero remainder. So, in this last part, this is recalled as remainder. So, in the Euclidean algorithm for f sub n plus 2 and f sub n plus 1. So, furnishes that the value of GCD, f sub n plus 2, f sub n plus 1. Hence, the GCD of this f sub n plus 2, f sub n plus 1 is just equals to f sub 2, which is 1. Right? So, next, some properties of Fibonacci numbers. The Fibonacci numbers have numerous easily derivable properties. One of the simplest, due to Edward Lucas, is that the sum of the r's and number equals sub n plus 2 minus 1. For instance, when we add the r's 8 Fibonacci numbers together, we get the total of 54. So, 54 is just equals to 55 minus 1. Where our 55 is our f sub 10. So, how to get f sub 10? So, we all know that f sub n is equals to 8. So, f sub n, or f sub 8 plus 2 is just equals to f sub 10. So, using this formula, where f sub n plus 2 is just f sub 10, then minus 1, our f sub 10 here is 55 minus 1. We can get the sum of the r's 8 Fibonacci number, which is 54. So, all in all, our conclusion are f sub 1 plus f sub 2 up to f sub n, where f sub n here is 8. This equals to f sub n plus 2, where f sub n plus 2 is f sub 10 minus f sub 2 is just equals to f sub n plus 2 minus 1. Another Fibonacci property of interest is the identity. So first, f sub n squared equals f sub n minus 1 times f sub n plus 1 plus negative 1 raised to the power of negative 1, where n here is greater than or equal to 2. And next, same equation, but f sub n here is 2k, where there is no raised to the power of n minus 1. So in this equation, let's say n is equals to 6 and n is equals to 7.
So, substitute from the given equation, our f sub n squared is magiging f sub 6 raised to the power of 2. As we can see, our f sub 6 in the sequence is 8, right? So, magiging 8 raised to the power of 2 na siya. So, as we can see in the equation above, our f sub n minus 1 is 5, right? Then, our f sub n plus 1 is 13. Then, negative 1 raised to the power of 6 minus 1 is magiging negative 1 raised to the power of 5. So, negative 1 raised to the power of 5 is magiging negative 1 lang siya. Then, it will become 5 times 13 minus 1, where 5 here is our f sub 5, and 13 here is our f sub 7 minus 1. Then next, our f sub n here is f sub 7. So, just follow the equation above. So, magiging f sub 7 squared. Then, yung f sub 7 natin sa sequence is 13, right? So, magiging 13 squared. Then, 13 squared is just equals to 8 times 21 plus 1, where 8 here is our f sub 6, then 21 here is our f sub 8, then plus 1. So, to establish identity, let us start with the equation f sub n squared minus f sub n minus 1 times f sub n plus 1. From this equation, ito'y magiging ganitong format, and then itong format na to is magiging close open parenthesis f sub n minus f sub n plus 1 and times f sub n minus 1 plus f sub n times f sub n minus 2, right? So, recalling that the rule of formation of the Fibonacci sequence, it gives like this, right? So, the expression in this parenthesis can be replaced by negative f sub n minus 1, right? To obtain this equation. Except for the initial sign of this equation, the right-hand side is just the same as the left-hand side, but with all the subscript decreased by 1, right? By an entirely similar argument, this equation can be shown to equal like this. Hence, to this equation is just similar to this equation, right? After n minus 1 such steps, we eventually arrive at like this. F sub n squared minus f sub n negative 1 times f sub n positive 1 is just equals to negative 1 raised to the power of n minus 2 times f sub 2 squared minus f sub 3 times f sub 1. And then, just copy the negative 1 raised to the power of n minus 2. Then, simplify using our Fibonacci sequence, which our f sub 2 is 1, f sub 3 is 2, and f sub 1 is 1. Just copy again, and 1 squared minus 2 times 1 is just equals to negative 1. So, from this, negative 1 raised to the power of n minus 2 times negative 1 is just equals to negative 1 raised to the power of n minus 1, which is what we sought to prove. So, for n is 2k, where k here is an integer. From this identity, so the relation becomes like this, where f sub 2k squared is just equals to f sub 2k minus 1 times f sub 2k plus 1 minus 1. This identity is the basis of a well-known geometric deception. As we can see in the diagram, the square here is 8 units by 8, while in the rectangle, 5 by 13. So, from this rectangle, makikita natin na yung side dito is 5, right? So, to accomplish this, divide the square into 4 parts as shown in the left-hand diagram, which is rectangle, and rearrange them as indicated on the right. So, the area of the square here is 64, right? Kasi i-multiply natin yung side by side. So, 8 times 8 equals 64. And then, sa rectangle, so 5 times 13 is just equals to 65. So from this, the area has apparently been increased by 1 square unit. The basal of this diagram is easily to explain, and the points A, B, C, and D here do not lie on the diagonal of the rectangle, but instead are the vertices of parallelogram whose area is exactly equal to the extra unit of area. Because the construction can be carried out with any square whose sides are equal to the Fibonacci number f sub 2k, from this diagram, change it like this. Diba kanina, yung f sub n natin is f sub 6, which is 8. So, yung f sub n natin or 8 is magiging f sub 2k na. Change everything in the diagram. So, yung 5 dito is magiging f sub 2k minus 1 na, right? And then, yung 3 dito is magiging f sub 2k minus 2. So, from this diagram of identity, we can now interpret that the area of rectangle minus the area of parallelogram is precisely equal to the area of the original square, right? So from this diagram, it can be shown that the height of parallelogram, that is, the width of the slat at its widest point, is this. So 1 divide square root of f sub 2k squared plus f sub 2k minus 1 squared. So using this formula, let's say na yung f sub 2k natin is reasonable odds. So for example, yung f sub 2k natin is 144. So kung 144 yung f sub 2k, so yung ating f sub 2k minus 2 is 55, right? So the slat is so narrow as to be almost imperceptible to the eye. This is a convenient to examine a remarkable between the Fibonacci numbers in what the Greek calls the golden ratio. So dito na pumapasok yung golden ratio. In mathematics, two quantities are in the golden ratio if the ratio is the same as the ratio of their sum to the larger of the two quantities. So, ibig sabihin nito na ang ratio ng dalawang value ay equal sa ratio ng total value sa pinakamalaking given value. So, using this formula, we can now get the u sub n. So, to find that, we need to divide the f sub n plus 1 into f sub n. So, for example here, yung u sub n natin is 1, so 1 divide 1 is just equals to 1, right? Another. So, yung u sub n natin is 2, so we need to divide the 2 divide 1 kasi yung 2 dito is our f sub n plus 1, then 1 dito is our f sub n. So, 2 divide 1 is just equals to 2. So, to find the u sub 3, u sub 4, u sub 5, and so on and so forth, always remember lang na i-divide lang natin yung f sub n plus 1 sa f sub n. So here in the u sub 8, dinidivide lang natin yung 34 sa 21. Yung 34 dito is our f sub n plus 1, then yung 21 is our f sub n. Para hindi kayo malito at maiintindihan palalo, kung hinahanap yung u sub 8, so i-divide lang natin yung f sub 9 sa f sub 8. So f sub 9 natin dito or f sub n plus 1 is 34. Then divide 21, which is f sub n or f sub 8. So it's just equals to 1.619. Dito, makikita natin na kung ang index is increases, yung sagot niya, it falls between 1.61 and 1.62, right? So let us assume that the limiting value actually exists. So call it like this. So for any n is greater than or equal to 1. So we have this formula. So which by the virtue of our definition of the UNs can be replaced by this. So UN is just equals to 1 plus 1 divided by u sub n minus 1. As n increases, the left and right hand sides of foregoing equation are getting closer and closer to golden ratio. So the formula of golden ratio is this, or just equals to 1.61 and so on and so forth. Thus, the sequence of the ratios of consecutive Fibonacci numbers gives an approximation of the golden ratio. And the farther out we go, the better the approximation becomes. So I think this is the last topic in our discussion. I hope you have learned something in our topic, the first awakening Fibonacci. And that's all. Thank you.